Hello everyone. In the last video, we looked into setup timing analysis and also we looked how does the presence of clock tree affected the setup timing analysis. Now let us try to look into hold timing analysis. We'll try to understand what is hold timing analysis and also we'll look what is the effect of the presence of real clocks, the presence of clock tree that we have built on the hold timing analysis and how critical it is. So let's start with that. Let's try to understand what is hold timing in this case. So for example, we have the same circuitry, we have the launch flop, we have the capture flop over here. So we have looked into one of the features of the flops which says that there is something called as setup time over here, which is nothing but the first mux delay. There is also something called as hold time over here, which is nothing but the second mux delay. And the hold time says that whenever we have a clock edge that comes over here that hits the capture flop, there is some finite amount of time required by the second mux which is present over here to process the data. Okay, we have looked into the structure of the flop in a separate section like VLSI Academy that has been conducted by us. So there we have looked into the internal of the flops. You might want to have a look into those lectures. But what happens is whenever you get a clock edge, the first thing we have looked into the setup timing, the amount of time that is required for the data to reach from this point to somewhere at the center of the flop. We have seen that, and that we call it as setup time. We have seen this in the last video. And there is one more thing that happens whenever let's say there is already an existing data at the center of the flop, and whenever a clock hits this particular flop, some finite amount of time is required for the data to process out of the flop. So there is a small amount, there is a mux present over here, which is again built of MOSFETs. So that those MOSFETs, those mux or those combinatorial logic will take some finite amount of time to come out from the middle of the flop to the Q pin. So that finite amount of time is called the hold time. Now let us look into the timing analysis, the hold timing analysis. So we have understood what is the hold time. So the timing analysis says something like this: you have this clock edge, you have the clock edge at zeroth time period, which is being sent to the launch flop clock endpoint, and the same clock edge is being sent to the capture flop clock endpoint. And this is quite different than the setup timing analysis. In the setup timing analysis, we used to send the zeroth clock edge at the launch flop and the clock edge at t time period at the capture flop. In this case, we send the same edge, the edge at the zeroth clock period at the launch flop clock endpoint and also at the capture flop clock endpoint, and then we do the analysis. This is a different kind of analysis compared to setup, and the same edge is being sent to the launch flop and the capture flop. Okay, now the analysis says that the combinational delay that we have between the launch flop and the capture flop, it should be greater than the hold time of the capture flop. So why? Obviously the reason is what we talked in some time back. Basically, whenever a data reaches at the D pin, previously the reaches the D pin, it eventually goes somewhere and sits somewhere at the center of the flop. Now there is some finite amount of time that this particular flop requires to send the data from the center point to the outside world. So that finite amount of time is called the hold time. Now the capture flop doesn't want to receive any kind of data when it's processing this data which is already present over here. Basically, while it is in the process to send the data which is present somewhere in the middle to the outside world, during that time the capture flop, this particular flop, doesn't want to accept any data. It wants to accept some data only when it finishes with its process. So this is the time required for the process, and it wants to accept data only when it finishes its process of hold time, whenever it finishes its process during the hold time. Hence the combinational delay, the delay from the delay of the data that is from this point to this point, it wants it to be greater than the hold time, greater than the processing time of the capture flop. So this is what is hold time. So it's very simple. This is a flop. It's doing some process inside it. During that time, it starts to do some process whenever it receives an edge. So when it receives this particular clock edge, it does some amount of process, and during that process, during that time that it is doing the process, it doesn't want to accept any kind of data, and hence we say that the delay, the data delay between the launch flop and the capture flop should be greater than the hold time of the capture flop, because it is doing some amount of job over here after it receives the clock pulse. Okay, so this was the hold time analysis. This is the basic hold time analysis with ideal clocks, but the clock time is 0. The time required for the clock to reach from this port to this point and from this port to this point is 0. That's why you see the launch clock, the clock edge is receiving at 0th clock time period. Now let us see the effect of the effect in the whole timing analysis when we add this clock. So it will be very simple. So before even getting into the diagrams, let's try to see what happens. So you have some clock buffers over here. The first thing that will happen, the 0th clock edge, which is the clock edge which is supposed to reach at 0th time period in the launch flop clock endpoint, that will get delayed. So there will be a shift for this particular clock edge. This particular clock edge will shift by some delta amount of period. So it will be this buffer delay plus there will be some buffer over here and the wire. So the clock edge that is received at the launch flop clock endpoint will be delayed by certain amount of time. So basically your complete this particular waveform will shift to the right side. Okay, now second thing, this particular clock edge will also get delayed to reach the capture flop clock endpoint, because you have the buffers over here, you will have some buffers over here, you will be having some buffers over here. So the clock edge that will receive over here, that will also get delayed. So similarly there you will see a shift in the 0th clock edge on the capture flop clock endpoint. Now after that, how does the equation changes? Let's look into that now. So we have these buffers, as we said, we have these buffers, we have this 0th clock edge, we have this clock edge which is supposed to reach at 0th clock time at the launch flop, but it won't. It will be reaching after a clock time period 1 plus 2. Okay, and the same edge will reach the capture flop at 1 plus 3 plus 4. So that was with the clock edge. At what time does the clock edge will be received at the launch flop clock endpoint and in the capture flop clock endpoint. Let us try to revise it first. So this particular clock edge will be coming at the launch flop clock endpoint after 1 plus 2 delay, and it will be received by the capture flop clock endpoint at 1 plus 3 plus 4. And as I said, the capture flop clock endpoint will start the processing of the data. Basically it will start to send the data which is present at the center of the flop to the outside world only when it receives the edge. So once the capture flop receives the data, receives the clock edge after 1 3 4, after 1 plus 3 plus 4 clock delay, at that time only it will start to process the data. So what does that mean? The capture flop will start to process its data only when it receives the clock edge, and the clock edge will be received at 1 plus 3 plus 4. So what you need to do is you need to just add 1 plus 3 plus 4 in the right hand side, because the whole time will start only after 1 plus 3 plus 4. Okay, and for the launch flop, the combinational delay will be coming into picture only after it receives this particular clock edge. And when will be this particular clock edge will be received at the launch flop clock endpoint? It will be after 1 plus 2. So the only thing that you need to do is add 1 plus 2 in the left hand side of the equation. So let's do that. So combinational delay plus the launch clock network delay should be greater than the whole time plus the capture clock network delay. So it should be something like this. 1 plus 2 is the time at which it receives the edge plus the combinational delay, and it should be greater than 1 plus 3 plus 4 when the capture flop receives the edge plus the processing time of the capture flop. So it's a very simple equation compared to the previous ones that we have seen. So what we'll do is next, so the 1 plus 2 will be calling it as delta 1, we'll be calling it as launch clock network delay, and 1 plus 3 plus 4 will be calling as delta 2, which is capture clock network delay. So skew, now when we say about skew, it's nothing but the launch clock network delay minus this capture clock network delay, and that should be 0. So that is basically what is skew about. So skew says that delta 1 minus delta 2 should be 0, should be close to 0, and if it is not, there are problems. The problems are pretty obvious from here. If you try to increase delta 2 even more by adding some buffers over here, the right hand side of the equation grows, the number at the right hand side of the equation grows even bigger. We'll look into that in some time from now. So the number on the right hand side grows even bigger, and it becomes difficult for the left hand side to catch up with the right hand side. So we'll look into this part of the equation also. So what we'll do is, since I'm already running out of time, we'll take this particular equation and we'll be adding some real values to this equation and making this equation a bit more practical compared to the VLSI chip. Let's try to do all this in the next video. Thank you.